Here are some problems related to ideal and actual regenerative Rankine cycle. So we are given in guided problem solving number 1 with a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius, and it is condensed in the condenser at the pressure of 10 kilopascal. Some steam leaves the turbine at 1.2 megapascal and enters the open feed water heater. Determine the fraction of steam extracted from the turbine and the thermal efficiency of the cycle. So for the schematic diagram of an ideal regenerative Rankine cycle with one open feed water heater, this is how it would look like. So we have the steam entering the turbine at 0.5 at a given pressure of 15 megapascal, and we have 600 degrees Celsius at 0.5. It enters the turbine and we extract, so we're given with a one open feed water heater, and steam is extracted, and the amount extracted, the fraction of steam extracted is given as y at this branch here at 0.6 going to the open feed water heater, and the remaining 1 minus y is condensed in the condenser. So this water that is condensed in the condenser, the steam condensed is pumped to 0.2, and it will meet the extracted steam at the open feed water heater. So this open feed water heater will heat somehow this fluid because of the extracted heat, heated steam. So as a result, we have 0.3, and 0.3 is pumped to the boiler pressure. So that is how our open feed water looks like. So as you can see, we have 7 points. We have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. So we tabulate all the known properties as well as the unknown. So all the known properties, they are in green. So for 0.1, so everything, we assume that the liquid, the steam, working fluid will exit the condenser at 0.1 as a saturated liquid. And it is given as the pressure of the condenser is 10 kPa. So the pressure at this branch here, 7 to 1, is the same. So the pressure on 7 and 1 is the same. So 0.1 is given as 10 kPa. That's why we have 10 kPa. And this is a saturated liquid, so the quality is 0. So for the mass flow rate, so take note that the extracted steam is y. So the remaining steam that will flow at this branch is 1 minus y. So when we multiply it with the mass that enters here, then that is the mass flow rate at 0.7 at the condenser. That's why it's mass times 1 minus y. At 0.2, so it is pumped to 0.2. So the pressure now is the same pressure as that of the open feed water heater, because for them to mix at the open feed water heater, they have to be at the same pressure. So that's why for 0.6, 0.2, and 0.3 to mix here, since open feed water heating is considered to be mixing also, then they have to be the same pressure. That's why 6, 3, and 2 have the same pressure. And since it is given as it is extracted at a pressure of 1.2 megapascal, so that's why 0.3, 0.2, and 0.6 have the same pressure. And that is 1,200 kilopascal. That's why we have 1,200 here. For the quality, that is a sub-cooled liquid. So no need to put that one. For the mass flow rate, as you can see here, the mass flow rate at 0.7 is the same mass that will flow at 0.1 and the same mass that will flow at 0.2 since there's no branching here. They are the same lines. So that's why the mass that will flow at 7, 1, and 2 is the same. So we have M1 minus Y. So that's why we have this mass flow rate here. So at 0.3, so as you can see, one of our assumptions also is that everything that will come out of the exit rather of our open feed water heater, it is assumed to be a saturated liquid. Since the exit is 0.3, that's why at 0.3 this is a saturated liquid. And the pressure again is the same as the pressure at 0.6 and 0.2. The quality is 0% since this is a saturated liquid. And for the mass flow rate, as you can see here, our 1 minus Y will meet with Y. So Y plus 1 minus Y, it will just be equals to 1. So therefore, at 0.3, our mass flow rate is just equals to M. So that's why we have here M. And this mass flow will be the same mass flow that will move in 0.4 and 0.5 since they are the same line and no branching at this point. So that's why we have our mass flow rate at 0.3, 4, and 5 is the same, and that is equals to M, as you can see here. Okay, so at 0.4, so it is pumped again. So from saturated liquid, it will become sub-cooled liquid at 0.4. So that's why we have here sub-cooled liquid after pumping. And now, the pressure after pumping, since the purpose of pumping is to increase the pressure, our pressure now will be at 0.4. As you can see, there is no pump in between these points. So meaning they have the same pressure. So for the fluid to flow here, we have the same pressure. So that's why our pressure at 0.4 is equals to the pressure at 0.5. And the pressure at 0.5 is given as 15 megapascal because it is the entrance of the turbine. As you can see here, the entrance of the turbine is 15 megapascal. That's why at 0.4 is 15,000 kilopascal also. And for 0.5, this is the point before it enters the turbine. So it has to be a superheated vapor, and it's given as 15 megapascal and 600 degrees Celsius. That's why we have the values here. At 0.6, so this is the point that we extract steam. Now we extract steam at this point. So we assume it first to be a superheated vapor, and we will check later on if it is really a superheated vapor. And the pressure for it is given as steam leaves the turbine at a pressure of 1.2 megapascal and enters the feed water heater. So that is this pressure here. So that's 1,200 kilopascal. Now for the mass flow, that since we have extracted Y here, then the mass flow rate will become M times Y. And finally, at 0.7, this is at the exit of the turbine at the condenser, and it is considered to be a mixture now. So the pressure is at 10 kilopascal since this is the same line without pump. So it's 10 kilopascal. So that is how you determine the different known quantities from the diagram and from the given problem. So we are going to determine now the different properties. So at 0.1, since this is a So if we're going to draw the TS diagram for this one, it will look like, so let's just draw it here. We have TS diagram. So at point 1, it enters as a saturated liquid. So since we are given with 3 pressures here, so we have 3 lines. So we have 15 megapascal, we have 1.2, and then we have 10 kPa or 0.01 megapascal. So our steam enters, it exits the condenser at point 1 a saturated liquid. So it's here. So this is the saturated liquid at point 1. So this is the point. So since this is saturated liquid, we can automatically use the software to get the temperature, entropy, and the enthalpy. So just substitute up, just plug in 10 kilopascal. And it is from process 1 to 2, it is pumping. So you pump it to a higher pressure, which is the pressure of the open feed water heater, that's 1.2. Since this is our we pump it at this point at the pressure. So this is our pressure line at this point. That's why we have it here. It has to be isentropic, so it's a straight line. So at point 2 is here. So since this is isentropic process, that they have the same entropy, 0.6492. And since we have entropy and pressure, and even though it's subcooled liquid, we can use these two quantity to get the other unknown. So we have it here. As you can see, there is a slight increase in temperature and also a slight increase in enthalpy after pumping. Next, at point 3. So point 3 is a saturated liquid at the pressure of the open feed water heater, which is 1.2. So our saturated liquid at that point is here. That's why we have it here. So since saturated liquid, we just automatically use the pressure to get the unknown quantity. So we have the quantities here. And then we have 3 to 4 is pumping again. So we pump it from 3 to 4 at the pressure of the boiler, which is 15 megapascal. So the pressure lines looks like that. So that's pumping, isentropic process. So we have a straight line once again, then we have it here. So it's still in the subcooled region. But the pressure now is the same pressure as that of our boiler, which is 15,000 kilopascal. And since 3 to 4 is an isentropic process, pumping, so that's why we have 2.2159 here. So now that we have pressure and entropy, we will use that to compute the unknown quantities. So at point 4, it is heated in the boiler to 0.5. So this process happens at isobaric process. So it became now superheated vapor after leaving the exit of our boiler. So say we have it here, superheated vapor. So we have superheated vapor at 15,000 kilopascal and 600 degrees Celsius. We can use these two values to get entropy and enthalpy. So we have this point. So we have this entropy and enthalpy. So for 0.6 and 0.7, since this happened, this process 6 and 7 is expansion. So our expansion is considered to be isentropic process. That's why our diagram looks like we expand it. So that's why we have a straight line once again. So this is our 0.5, then we have here at 0.6, then we have 0.7 here. So for point 6, you can see that they have the same entropy, 5, 6, and 7. So we can use that value, that entropy, as well as the pressure at point 6 to get the other unknown. And same also with 7, since this is isentropic process. So 5, 6, and 7 have the same entropy. And use the pressure to get the temperature and the enthalpy. So this is the TS diagram. We have point 1, 2, 3, 4, 5, 6, and 7. This is for the open feed water heat. So to determine the fraction of steam extracted from the turbine, so we can easily get that by doing an energy balance in the open feed water heater. So this is the where we can get the value of Y. So by using energy balance at the open feed water heater, so since we have here mass flow rate at 0.6 as well as the enthalpy at, so M6H6, we have that as the energy that entering here, and we also have an arrow here that's M2H2, and then the one that exiting is M3H3. So we isolate this open feed water heater and create energy balance of these values, M6H6, M2H2, and M3H3. So energy in is equals to energy out. So we have M6H6, so plus M2H2 is equals to M3H3. So our entrances are 6 and 2, and the exit is 0.3 for the open feed water heater. That's why we have this energy balance. And if you look at our table, we will have to get the value of M6 in terms of M. So M6 is My. Our M2 is equals to M1 minus Y. Our M3 is equals to M. So we substitute that here in the formula. So we have, so M6 is My, M2 is M1 minus Y, M3 is M. So that's why we have this one. As you can see, we can cancel out mass since they are appearing in all terms. So we are left with this one. And finally, we can use, so we expand that and then isolate Y so that we can get the equation for Y in terms of the enthalpies. Since we already have the enthalpies, then we just substitute those. So our Y is equals to 0.2271. So meaning the fraction of steam extracted at 0.6 is 0.2271. And 1 minus Y is the steam that flows at 0.7 and at 0.1 and at 0.2. So our Y is 0.2271. This is the fraction of steam extracted for the open feed water heater. To determine the thermal efficiency, we just use our equation. Thermal efficiency is equals to 1 minus Q out over Q in. If you are going to look at our diagram, so our Q out is the heat rejected at the condenser. Our Q in is the heat that we absorb in the boiler. So in green, this green one here are the work, and then the red arrows represents the heat. So heat rejected in the condenser, that's our Q out. Heat input in the boiler is our Q in. So that's why we will use the enthalpies at that point multiplied by the mass flow rate. So we can write 1 minus Q out. So our Q out here is our mass flow rate M4. So our Q out is, if we're going to have our energy balance at the boiler, that is equals to M4H4 plus our Q in is equals to M5H5. So our unknown is the Q in, so our Q in is just equals to mass flow rate times H5 minus H4. Take note that the mass flow rate here and at 4 and 5 is the same since there's no branching here. So 4 and 5 have the same mass, and that is m. So that's why we can just cancel out m because m will appear both in the denominator and numerator here. Since our this is for our Q in. For our Q out, so it is at the condenser. The mass flow rate here is different. That is 1 minus y. So that's why for that point, we can use H7 plus is equals to, so in our out are our Q out, of course, plus M1 H1. So our M1 and M7, that is equals to M1 minus y. That's why our Q out will become 1 minus y, H7 minus H1. So that's why our Q out is equals to M H7 minus H1. Since our M is equals to 1 minus y, that's why we have here 1 minus y. That is for the thermal efficiency. So we can easily get the thermal efficiency by using energy balance. So by substituting the value of enthalpy as well as the value of y, our thermal efficiency is equals to 46.31%. So as you can see, this is an increase from our efficiency as compared to our simple Rankine cycle as well as the reheat Rankine cycle. Guided problem solving number 2. So in here, we are given with a steam power plant that operates on ideal regenerative Rankine cycle. But this time, we have a closed feed water heater. So the plant maintains the turbine inlet at 3000 kilopascal and 350 degrees Celsius and operates the condenser at 20 kPa. Steam is extracted at 1000 kilopascal to serve the closed feed water heater, which discharges into the condenser after being throttled to condenser pressure. Calculate the work produced by the turbine, the work consumed by the pump, the heat supply in the boiler for the cycle per unit of boiler flow rate. So as you can see here, this is our diagram for this problem. So we are given with a steam power plant that enters at point 4 at 3000 kilopascal and 350 degrees Celsius. So this is the pressure and temperature at point 4, and then it operates at a condenser pressure of 20 kilopascal. So that's why we have here 20 kilopascal at the condenser. The steam is extracted at 1000 kPa. So that's why we have here 1 megapascal to serve the closed feed water heater. So we extract steam at 0.5 to serve the closed feed water heater, as you can see here. And then it discharges. So the discharge of the closed feed water heater is to the condenser after being throttled. So meaning we use a throttling device, a pressure reducing valve, to reduce the pressure from discharge the extracted feed water heat to the feed water heater. So we have here 0.7. Guided problem solving number 2. Consider a steam power plant that operates on ideal regenerative Rankine cycle with a closed feed water heater as shown in the figure. So the plant maintains the turbine at 3,000 kilopascal and 350 degrees Celsius. So that means that the inlet of the turbine, and that is 0.4, the pressure is 3,000 kilopascal and the pressure is 350 degrees Celsius. And the condenser is at 20 kilopascal. So the condenser is at 20 kilopascal. Steam is extracted at 1,000 kilopascal. So steam is extracted at 0.5 at 1 kilopascal or 1 megapascal. Serve our closed feed water heater. And it discharges the discharge, since our closed feed water heater is a non-mixing heater, it has to discharge. It cannot mix with the fluid at 0.2. It has to discharge from the closed feed water heater. So it discharge it into the condenser. That's why we have here from 0.5 we discharge it at 0.7 using a throttling device, a pressure reducing valve. So we discharge it to the condenser pressure. So from 7 we discharge it to 8, so that the pressure now will become the same pressure as the condenser. And then we are to calculate the work produced by the turbine, the work consumed by the pump, the heat supply in the boiler for this cycle per unit of boiler flow rate. So you can also see here the TS diagram. So as you can see, 0.1 to 2, we pump it. So we have from a saturated liquid to 0.1, we pump it to 0.2. And then at 0.2, it is now a subcooled liquid. And it, since closed feed water heater is non-mixing, so 0.2 here will not mix with 0.5. So they are non-mixing. They will just heat exchange, but they will not mix. That's why 0.2 has the same pressure as 0.3. It just the same line. So after pumping, 0.2 will have the same pressure at 0.3. That's why it's connected here to the pressure also at the boiler. So 0.2, 0.3, 0.4 have the same pressure since they do not mix at the closed feed water heater. And then for 0.4, it is entrance of the turbine. So that is a superheated vapor. And then it expands at 0.5 and 6. So we have here isentropic expansion 5 and 6. Then at 0.5, this is where we extract value of y. And then the remaining 1 minus y is the one that flows in the condenser and the pump. So we are going to tabulate the known quantities for us to get the unknown. So at 0.1, this is a saturated liquid, as you can see here. And we are given with a pressure of 20 kilopascal. And since this is a saturated liquid, and then we have a one known quantity, we can get the unknown. And then at 0.2, since 1 to 2 is isentropic pumping, so we have here, we have the same entropy. Since we have entropy and pressure, we can use those two quantities to get the unknown for the subcooled liquid. Then at 0.4, we can get first the 0.4 because we do not know yet. Since this is subcooled and we only have one known quantity, we cannot yet get the value for this 0.3. So we'll solve first 0.4. So 0.4 we're given with two value. So we will use that to get the entropy as well as the enthalpy. And then at 0.5, so 0.5 is, this is the extraction So as you can see here, extracted at 0.5 at 1000 kilopascal. That's why we have here 1000. And since 4 and 5 have the same entropy, that's why we can use that entropy and the pressure to get the unknown at 0.5. And then we have at 0.6, 0.6, 0.5, and 0.4, as you can see here in the diagram. 0.4, 0.5, and 0.6 is a straight line, so that is isentropic process. So that is the same entropy, 4, 5, and 6. Then we use the pressure at 0.6, which is the pressure at the condenser, and that is as 20 kilopascal. So 20 and 6.7449, we can get the temperature as well as the enthalpy. At 0.7, since 7 is the discharge point of the closed feed water heater, that is assumed to be a saturated liquid. So as you can see here, it discharges at 0.7 as saturated liquid. So that is the same pressure as 0.5. Since this is a horizontal line, that's 1 megapascal. So using 1 megapascal and saturated liquid, we can use the saturation points to get the value of temperature, entropy, and enthalpy. And for 0.8, since 7 to 8, so as you can see here, this is a pressure reducing valve. It is throttled, it's throttled from 0.7 because it has to discharge, because it's a closed feed water heater. Its discharge is towards the condenser. So this is our 0.8, therefore is a mixture. As you can see here in the diagram, it's a mixture at the 20 kilopascal saturation. So that's why the pressure is 20 kilopascal. And since this is a throttling process, and that is considered to be constant enthalpy. So 7 to 8 is constant enthalpy. So that's why our enthalpy on 7 and 8 is the same. So we have 762.52. And for the temperature, so we can use this pressure and enthalpy to get that. And since this is a saturation region, it's just the same as 0.1. So 1, 8, and 6 have the same. So 1, 8, and 6, they have the same pressure. 7 and 5, they have the same pressure. 7, and 5. Yes, they have the same pressure. That's 1000. But the temperature is 7 and 5. They have the same. They have different temperature, as you can see. So now for the 0.3, one of the assumption is that the outlets of the closed feed water heater have the same temperature. So the outlets are 3 and 7. That's why 0.3 and 7 have the same temperature. So 0.7 is 179.88. Therefore, 0.3 is also 179.88. And using this pressure and temperature, we can get the enthalpy as 763.54. So we get all the enthalpies. So for the mass, as you can see here, at 0.4, it is considered to be M. And it's extracted at 0.5 at Y. So 0.5 will become My. At 0.6, the remaining will become 1 minus Y. So that is M1 minus Y. As you can see here, our 0.5 is My. So we have My here. And since 0.5 will not mix with 2, so 0.5 will just discharge it at 7 without mixing at the 0.2. So the entrance are 5 and 2, but 2 and 5 will not mix. So they are different lines. That's why 5 is just the same as 7. So that's why M5 is equals to M7, and that is My. And M7, there's no branching here, so it's just the same. So M8 is also My. For the condenser, so as you can see here, what the entrance of the condenser is our My and M1 minus Y. So when you add that, My plus M1 minus Y, the result will become M. So at point 1, it will become M. And then if pump it at point 2, that's still M. Since 2 will not mix with 5 at the closed feed water heater, that is close. So 2 will just become just the same mass flow rate as 3, so that's M. And there's no branching here, so that's still M. 4. So that's how you analyze for the mass flow rate at the different points using the closed fed water heater. You just have to take note that the fluid that will enter the closed fed water heater will not mix. So 5 will not mix with, so 2 will just enter and then goes out as 3, 5 will enter and goes out as 7. So they are different types. So now we can calculate for the unknown. The first one is the fraction of steam extracted at 0.5. It is necessary to determine first the fraction of steam extracted at 0.5 because this will help us get the mass flow rate at the different points. So again, we are going to use energy balance at the closed feed water heater. So using energy balance at the closed fed water heater, you can see here that we are entering at 0.5 as M5H5. And then here we have entering also from the pump 1 to 2, that is M2H2. And then this M5H5 will just be connected to, it will discharge at 7, so that's M7H7. And 2 will be discharged as M3H3. So these are the energies that's taking heat exchange in the closed fed water heater. Line 2 to 3 is doing heat exchange with line 5 to 7. So basically, since 5 is hot, so it will increase the enthalpy and temperature of 0.2 to 3. So that's what closed fed water heater does. So using energy balance, energy in is equals to energy out. Our entering are 5 and 2. So that's why we have M5H5 plus M2H2. And exiting are 0.3 and 0.7. So we have M3H3 plus M7H7. So we substitute the masses here in the table. M5 is equals to My. M2 is equals to M. M3 is equals to M. M7 is equals to My. So substituting the value, we have this one. And then since M is common, we can cancel out that one. And then we just solve for the value of Y. And since enthalpies are already here in the table, we just plug it in so that our fraction of steam extracted at 0.5 is 0.2436. So we extract here steam of 0.2436 of the total M that enters. So if this is M, so extract here 0.2436 M, and then what's remaining here for 0.6 is 1 minus 0.2436 times M. So that's how the extraction happens at the turbine for our feed water heater. So now we can calculate for the work produced by the turbine. So the work produced by the turbine, it is given by this arrow, so meaning it has a work output, it's going out. So the green arrows here represents the work, the red represents the heat. So we have here output, so we have work output in the turbine, and then we have work input in the pump. We have heat rejected or output in the condenser and heat input in the boiler. So for the work produced, that is the work output of the turbine. So the work produced by the turbine, we can get that by doing energy balance here. in the turbine. As you can see, we have M4H4 entering. So M4H4. Then we have it's going out at 0.5 as M5H5 and at 0.6 as M6H6. And then we have outgoing also work here by the arrow. We're going to do energy balance of those energies. So energy in, energy out. So energy in is our, as you can see here, the only arrow that's entering is 4. So we have M4H4. So ang mga our energy going out of the turbine is at 5 and 6, and the work output is going out. So that's why we have M5H5 as M6H6 plus work output of the turbine. So do not forget to include the work output of the turbine in the energy out. And then we're going to substitute the, since our work output in the turbine in terms of we are going to extract mass, it's just equals to MWT. So we are going to substitute the values of masses of 4, 5, and 6 here in the table. So that's why we have this one. So we can cancel out all the masses. That's why we have this one. But the work output of the turbine is just H4 minus Y, H5 minus 1 minus Y, H6. And since Y is 0.246, H4, H5, and 6 are already in the table, we can get the work produced by the turbine by substituting those values. So the work produced by the turbine is equals to 741 kilojoules per kilogram. Next one is the work consumed by the pump. So the work consumed by the pump. So as you can see here, we have energy entering M1H1, energy going out from the pump M2H2, and then this work is work in, so it's going in to the pump. So energy in, energy out in the pump gives us M1H1 plus our work pump, which is entering, equals to energy going out, that is M2H2. Since our M1 and M2 are given in the table as M, we can join them together as M. So we can cancel out M here. So our relationship will become this one. So our work of the pump is just H2 minus H1. Since we already have the enthalpies, then we can get the value of the work consumed by the pump by substituting the values in the table. And that is negative 3.03 kilojoules per kilogram. So the negative sign means it's needing work. It's needing electricity work. So we need to use 3.03 kilojoules per kilogram to make our pump work. For the heat supplied in the boiler, so as you can see here, we have energy entering as M3H3 and energy exiting as M4H4. And then we have heat here going in because we are putting here energies from fuels. So that's why we have, for energy balance, energy in is equals to energy out. Energy in is M3H3 plus the heat input in the boiler. Energy out is our M4H4. So substituting the masses from the table and canceling out those masses since they are the same, our Q of the boiler, or heat input or supplied in the boiler, is just H4 minus H3. So substituting the value of enthalpies from the table, our heat supplied or input in the boiler is equals to 2,353 kilojoules per kilogram. So this is the amount of energy we derive from the fuel for the boiler. And finally, for the thermal efficiency, we are just going to use the formula work net over Q in. So our work net is equals to the work of the turbine minus work of the pump. Our Q in is the heat input in the boiler. So substituting those values, so our thermal efficiency is 31.36%. Guided problem solving number 3. Consider an ideal steam regenerative Rankine cycle with 2 feed water heaters. So we have one closed and one open. Steam enters the turbine at 10 megapascal and 600 degrees Celsius. That's why we have here at 0.8, it enters the turbine at 10 megapascal and 600 degrees Celsius at 0.8. And exhaust to the condenser at 10 kPa. So the pressure in the condenser is 10 kPa. That's why we have here 10 kPa. This is the condenser part in our TS diagram. Steam is extracted from the turbine at 1.2 megawatt for the closed feed water heater. So steam, to extract steam at the amount of Y at 0.9 to the closed feed water heater, as you can see here. And that is happening at 1,200 kilopascal or 1.2 megapascal. That's why you can see here, it extracted turbine at 0.9 at 1.2 megapascal for the closed feed water heater. And then also extracted at 0.6 megapascal for the open. So you can see here, we extract Z, a Z amount of steam at 0.10 for the open feed water heater, as you can see here. And that's happening at 0.6 megapascal. So we extract at 0.10 at 0.6 megapascal. The feed water heater is supplied to a condensation temperature of the extracted steam in the closed feed water heater. So the extracted steam leaves the closed feed water heater as saturated liquid. It leaves at this line here as saturated liquid at 0.6 as saturated liquid. So 0.6 here is saturated liquid, which is subsequently throttled to the open feed water heater. As you can see here, at 0.6 we throttle it using a pressure reducing valve to the open feed water heater. So meaning from 1.2 megapascal, we reduce the pressure, since this is a pressure reducing valve, to the pressure of the open fed water heater so that it will enter this one. So we have here 0.6, it's happening at throttling, so that's isenthalpic process, so 6 to 7. So 6 to 7 here is a throttling process, and it's throttled to the open feed water heater, which is at 0.6 megapascal. That's why it looks here. So we are going to determine the mass flow rate of the steam through the boiler for a net power output of 400 megawatt and the thermal efficiency of the cycle. So this is how the diagram looks. So at point 1, so that is saturated liquid at the exit of the condenser, and it is pumped. Point 2, as you can see here, to become subcooled liquid, and it enters the open feed water heater. Take note that open feed water heater is mixing. Therefore, all the fluid that enters here has to be the same pressure for them to mix. Otherwise, they will not mix. So for them to mix, point 2, point 7, point 10, and point 3 should have the same pressure. So that's why 2, 3, 7, and 10, 2, 3, 7, and 10 should be the same pressure. As you can see here, it's the constant pressure lines 0.6 megapascal. 2, 3, 7, and 10 have the same pressure. And at point it exits, all the entering fluid will enter the open fed water heater 1027 and it will exit at point 3 here in the TS diagram. Then after that, it will have to be pumped again. So since the pressure is in 6 megapascal, for it to mix, for us to raise it to the boiler pressure, we have to pump it. So at point 3, we pump it to 0.4. As you can see here, we pump it to 0.4. That's why it became a subcooled liquid at 0.4. And it enters it here. It is now here at the entrance of the closed fed water heater. And since the closed fed water heater is not mixing, 0.4 does not have to be the same pressure as 0.9. So 4 and 9, they have the different pressure. That's why you can see here that 4 and 9, they do not the same. They don't belong to the same line, unlike here. So it's only 9 and 6 have the same pressure because this is the line connecting the 0.9 to 0.6, the entrance and the discharge from this extraction. So this is a closed fed water heater, meaning 4 will just go out the same pressure at 0.5 and the same pressure at 0.8. So 8, 5, and 4 have the same pressure since there's no pumping anymore here and there's no mixing. So 8, 5, and 4 have the same pressure. That's why it automatically 4, 5, and 8 are at 10 megapascal. As you can see here, they're 10 megapascal. And then, so now it is at 0.5 entering the boiler. At here, as you can see in the TS diagram, we just assigned it here because we do not know where it is really. And then we added heat in the boiler, heating the steam to 0.8. It will making it superheated vapor at the entrance of the turbine. And then it will expand to 0.9, 10, and 11 here, as you can see. 9, 10, and 11 at the exits of the turbine. So we are going to tabulate all the points to get all of the unknown. So we can see here 11 points. So for point 1, this is here in the TS diagram, is a saturated liquid at the condenser pressure. And the condenser pressure is 10 kilopascal based on the given. So since this is saturated liquid, all we have to do is just to plug in that value. We can get the temperature, entropy, and enthalpy. Process 1 to 2 is pumping, as you can see here in the diagram. That is isentropic process, but they have the same entropy. And since we have entropy and pressure, we can get also the temperature and enthalpies. At point 3, this is a saturated liquid. So at point 3 here, so this is a saturated liquid at point 3 because this is after our extraction from the open fed water heater, it will come out as saturated liquid. So point 3 is a saturated liquid but at a pressure of 600 kilopascal. So we have here 600 kilopascal. Then use that knowledge to get temperature, entropy, and enthalpy. 3 to 4. So 3 to 4 is pumping. So that is isentropic process. So 3 and 4 have the same entropy. So using 2 value, we can get temperature and enthalpy as well. For 0.5, we know that that is a subcooled liquid because as you can see here in the diagram, it's a subcooled liquid. But we only know that the pressure is the same as 4 and the same as 8 because again, 4, 5, and 8 is just the same line and there's no pumping here. And 4 doesn't mix with 9, that's why it remains its pressure to be 10 megapascal. So that's why the pressure at 0.5 is 10,000 kilopascal. But we do not know other quantities yet, so we cannot solve 5 yet. So we will proceed with 0.6. Since 0.6 is Since 0.6 is the discharge of the closed feed water heater, it is a saturated liquid. As you can see here, it discharged from 9 to 6, a saturated liquid. So 9 to 6 discharge a saturated liquid at 1.2 megapascal. So we can use this saturated liquid and pressure to get the other values. So one of our assumption now is that the discharge of the closed feed water is just the same. So therefore, temperature at 0.6 is just the same temperature at 0.5. So that's why we can use this temperature here as the same temperature at 0.5. And then we can use this 2 value now to get all of the unknown for 0.5. At 0.7, as you can see, this is 6 to 7 is throttling. Throttling is isenthalpic process. So 6 and 7 have the same enthalpy. So we have here 798.33. In 0.8, we're given with a superheated vapor with 2 properties. So we can get the other properties. And then we can see that 8, 9, and 10, and 11 is a straight line, meaning that it's isentropic process. Therefore, they have the same entropy. And since we have entropies and other values here, we can get the other quantities using our software. So by that, we are able to complete the table. For the masses, so since M enters at 0.8 and is extracted as Y, Z, and Y minus 1 minus Y minus Z. So at 0.1, you can see here, it's the same mass flow at 0.11. The mass flow at 0.11 is 1 minus Y minus Z, because we extracted Y here at 9, extracted Z here at 10, so the remaining will be 1 minus Y minus Z. That's why the mass flow rate at 11 and 0.1 is 1 minus Y minus Z times M, as you can see here. As well as when you pump it, so there's no branching here, so it's just the same at 0.2, 1 minus Y minus Z. At 0.3, as you can see here, first we go to 0.9. So at 0.9, we extract Y, so we have here at 0.9 as My. At 0.10, we extract Z, so we have Mz. Since 0.9 do not mix with 4, then 9 will just go out at 6 as the same mass. So M9 and 6 have the same mass. So that's My. And then 6, since there's no branching here, will just be the same mass as 7. So that's also My at 7. So now, at the open feed water heater, we have My plus My minus 1 minus Y minus Z plus Mz. So we have open feed water heater, we have My plus we have 1 minus Y minus Z times mass as Z here entering at 0.10 as Mz. If you're going to take the sum of that, you can see that at 0.3, it is just equals to M. So that's why at 0.3, our mass flow rate is just equals to M. Because all the masses will begin to add again here at open feed water heater, because this is mixing. So 7, 2, and 10 will mix here. All those masses will accumulate and will become mass again. And then since 0.3 is M, and then it's pumped to 0.3 without branching, so it's just M at 0.4. And since it is a closed feed water heater here, it will not mix. So 4 and 5 have the same mass. So M5 is also M. And finally, there's no branching here. 8 and 5 will just equals to mass, or M. So those are the masses in the different branches. So first, in solving regenerative Rankine cycle, we really have to compute for the extractions. So we need to compute for the extractions before we can calculate all the unknowns. That's why after tabulating all the properties, the first step is really to determine the rate of extraction. So we are going to do energy balance at the closed fed water heater and energy balance at the open fed water heater. So for the closed fed water heater, our energy entering are M4H4. We have entering at 0.4, entering at 0.9, and exiting here are 6 and 5. So this is entering, this is entering. 5 and 6 are exiting. So that's why we have M4H4 plus M9H9, energy in, energy out are 6 and 5. So this is 5. And then substituting the values of mass from the table, we have this one. Canceling out the masses since they're the same. So our y is equals to H6 minus H4 over H9 minus H6. So our y is just equals to 0.05406. The rate of extraction at point 10, we are going to do energy balance in the open fed water heater. So as you can see here, the energy entering are 0.2, 0.10 based on the arrow, and 0.7. And the energy exiting is 0.3. So that's why we have energy balance at the open fed water heater. We have M10H10 plus M7H7 plus M2H2 is equals to M3H3. So substituting the masses here in the table and canceling common mass. So we are left with this one. So we just substitute the enthalpies and the value of y that we computed earlier. And then our only unknown is z. So you can use algebraic manipulation to solve for z, and z is equals to 0.1694. So the rate of extraction at point 9 is 0.05406, and z, the rate of extraction at point 10 is 0.1694. So we can now calculate the unknown. The first one is the mass flow rate of steam through the boiler for a net power output of 400 megawatt. So using energy balance in the entire power plant, as you can see here, our energy in are the boiler, the pump work, so these are energy in, and our energy out are the turbine and the condenser because it's rejecting. So using energy balance, so we have Q boiler plus work pump 1 plus work pump 2. So these are energy in. Energy out are work of the turbine plus heat rejection at the condenser. So rearranging that, our heat input in the boiler minus heat output in the condenser is just equals to the work of the turbine minus work of the pumps. And since our work net is just equals to work of the turbine minus work of the pump, then our work net will just be equals to heat input in the boiler minus heat rejection at the condenser. So our work net can be written as, so our heat input in the boiler is just equals to mass flow rate at the boiler, that is M, multiplied by that enthalpy difference, that's H8 minus H5. For the condenser, the mass flow in the condenser is equals to 1 minus y minus z. You can see here at 0.1, 0.2, and 0.11. So that is 1 minus y minus z. That's why the mass flow rate is multiply those extractions multiplied by the enthalpy difference at the condenser, which is H11 minus H1. So that is H11 minus H1. Mass flow rate is 1 minus y minus z. That's why we have these values here. So our mass flow rate is just equals to work net divided by this value if we rearrange this one. Since we already have a work net that is given as 400 megawatt, and we already have yz and the enthalpies, we just substitute those values and solve for the mass flow rate. So the mass flow rate of steam through the boiler is 314 kilogram per second. So this is per second, there is 314 kilogram of steam flowing through the boiler. So that's an enormous amount of steam. For the thermal efficiency of the cycle, we can use work net over Q in. Since our work net is given as 400 megawatt, and our Q in is just the heat it put in the boiler, which is the same QB. So we just substitute that value here. And then the mass flow rate, since so that will have the same unit, we can cancel out the units. So our thermal efficiency for the cycle is 45%. That is also a good thermal. Guided problem solving number 4. A steam power plant produces 1,000 megawatt of electricity while operating on three-stage regenerative cycle. The steam enters the turbine at 14 megapascal and 580 degrees Celsius. That is at 0.9. And extraction occur at 2.5 megapascal. So this is at 0.10. 700 kilopascal at 0.11. And then extraction at 0.12 at 150 kilopascal. And the turbine exhausts at 15 kilopascal. So it exhausts at 0.13 at 15 kilopascal. So we have here 2.5 megapascal. Here at 0.11 we have 700 kilopascal. At 0.12 we have 150. And the pressure at 0.13 is 15 kilopascal. We have 3 extractions because we have 3 open feed water heater, as you can see here. So feed water heater 1, feed water heater 2, and feed water heater 3. And then our turbine has an internal efficiency of 92%, which means its isentropic efficiency is 92%. So we are dealing here with an actual regenerative Rankine cycle with isentropic efficiency for the turbine given. This is the diagram for a 3-stage regenerative Rankine cycle. We have open feed water heater 1, 2, and 3. So we are going to determine the mass flow rate, the heat supplied, the fuel flow rate if the energy release is 35,000, the mass fractions y, x, y, and z, and the cycle efficiency. As you can see here, we have different points, and we're going to tabulate, determine the enthalpies at the various points. So we have 13 points. So we are going to use this diagram to determine the properties at the different points. So for open feed water heater, since our fluid will mix, so they will have the same pressure. The points that will mix at that heater will have the same pressure. And for us to connect it to another component, we have to pump it. That's why we have pumps after the feed water heater. So let's start with point 1. So at point 1, we have, so everything now that after the condenser, it will always be saturated liquid. That's why we have here saturated liquid, and the pressure is given in the problem that the pressure in the condenser is 50. So meaning the pressure also of the points connected to the condenser is 15. So point 1 is 15 kilopascal. So that's why we have here 15 kilopascal saturated liquid. So we can determine that properties directly. And then it is pumped to point 2. So pumping it would make it a subcooled liquid. So that's why it is a subcooled liquid, and then it is pumped to the pressure of the feed water 1. So now it is connected to your feed water 1. So point 1, point 3, and point 12. So they are connected to the feed water 1 and they will have the same pressure. And since the pressure at point 12 is 150, so meaning the pressure at point 2 is also 150. For them to mix, it has to be the same pressure. Again, open feed water heater includes mixing. That's why it's 150. And since process 1 to 2 is isentropic, that's why they have the same entropy as point 1. And since we have two known property, we can get the remaining properties using the software. And now at point 3. So as you can see, point 3 is leaving the feed water heater so that it will be pumped. So in our assumption, when it leaves the feed water, open feed water, it is now a saturated liquid. So point 3 is a saturated liquid with the same pressure as point 12 because they are connected to the same feed water. That's why they will have the same pressure, but this time it's a saturated liquid at point 3. So since it's saturated, we can get the properties directly using the software. And then from 3, we pump it to point 4. So it will increase the pressure. And this time, the pressure at point 4 is the same pressure as the fed water 2 and the point 5 and point 11. Pressure at point 11 is 700 kPa from the given. So it has the same pressure for them to mix at the feed water heater. That's why it's 700 kPa. And since 3 to 4 is pumping, so this is isentropic. So we are given with the same value as point 3. And then using these two values, we can get the remaining values. At point 5 now, it will leave again the feed water just like point 3. So when it leaves the feed water, it will have saturated liquid. So point 5 is saturated liquid. And the same pressure as point 11 because they are on the same feed water. So it's still 700. We can use this known so that we can get the unknown from our software. And then you can see that 5 to 6 is pumping. So that's isentropic. So they have the same entropy. And for 0.6, the pressure is the same pressure as the fed water 3 and the 0.10 and 0.7 because they are connected. So 10, 7, 6 have the same pressure and that is given from the problem as 2,500 kPa. And since we have two known here, we can get the other unknown from the software. And then 7 is leaving the feed water 3, so it should be saturated. So that's why we have a saturated liquid at the same pressure of 2,500 kPa. And since this is saturated, we can get the other properties. And then at point 8, 7 to 8 is pumping, so that's isentropic process. And since at point 8 now, the pressure it is connected to the boiler, which is connected to point 9. And point 10 is given as 14,000 kilopascal. So boiler, point 10, and point 8 have the same pressure. So that's 14,000. So using these two values, we can get the other unknown. And then at point 9, it is entering the turbine at 14,000 kilopascal and 580 degrees Celsius from the given. That's why we can get the different unknown as well because we have two values. And then from point 9, you are going to expand it in the turbine to points 10, 11, 12, and 13. Expansion is isentropic process, so meaning point 9 have the same entropy as 10, 11, 12, and 13. And since you have two knowns here in these points, then you can get the remaining unknown. So that's how you can complete that table. that we will need for our solution later on. For the mass flow at the different points, first we are going to look at point 9. It enters point 9 as one, no? As a whole mass of steam. Then it will be extracted at point 10 as x. So meaning the flow at point 10 will be mx. So we have here point 10. Point 10, okay. It should be mx here. Or you can actually interchange so 10 should be mx. This is mx. Yeah. And then at point 11, we extract another portion, that's y. So the flow at point 11 is my. That's why we have your my. At point 12, we extract z. So that's why we have mz here. And then at 13, because of the extraction, the remaining here will become 1 minus x minus y minus z. It will become 1 minus x minus y minus z times the mass flow rate. So you can see now that point 13, point 1, and point 2 have the same mass flow. So that's why point 13, point 1, and point 2 have the same mass flow rate. Then you can also see that point 2 and 12 will mix. And since our 2 is 1 minus x minus y minus z, and 12 is z, then they will add up. So the resulting will be 0.3. So when you add that, the result will be 1 minus x minus y. So at point 3 now will become m 1 minus x minus y. It will flow to the pump, and the same flow will be for 0.4. That's why 0.4 will still be 1 minus x minus y. Now at 0.4, 1 minus x minus y will be added by y. So we can eliminate y. The result will become 1 minus x at 0.5. So it will exit at 0.5 as 1 minus x. And then it will flow to the pump 3. So 0.6 will be the same as 0.5. So that is 1 minus x. 1 minus x will now sum up with x. So that will result 1. So at 0.7, the mass flow rate will just become m. So that's why it's m here. And then it will flow to 0.8, still at m, and 0.9 still at m. So that is the mass flow rate at the different points. So as you can see here, our different points and the different enthalpies and mass flow rates are tabulated. First, we're going to solve for the actual value of enthalpies. Because this problem is an actual cycle, we are given with isentropic efficiency for the turbine. So we are going to use that to get the actual value of enthalpies at point 10, point 11, point 12, and point 13. Because in the actual process, it will be different as the ideal, because it will look like this. So we have instead of having this isentropic process from point 9 to point 13, we have your point 9, 10, 11, 12, and 13. It will be isentropic. It will have isentropic efficiency. It will deviate. So it will deviate, so meaning 10, 11, 12, and 13 will not be the same. So we have to compute for the actual value of 10, 11, 12, and 13 as a result of the isentropic efficiency of the turbine. The same also if we are given with isentropic efficiency of the pump, we will use the pump relationship for isentropic efficiency, which is the same that we discussed before for actual cycle. You can go back to the topic to recall how to compute isentropic values. Using isentropic efficiency of the turbine, which is 92% based on the problem. So our isentropic efficiency for the turbine is defined as actual work divided by the isentropic work of the turbine, or WS. So for expansion 9 to 10, this will become H9 minus H10 actual divided by H9 minus H10. So this actual here is the one that we are looking for. So the actual value of 0.10. If we substitute 9 and 10 from this table and solve for H10, our H10 just is 3059.02. As you can see, it is larger than the isentropic value, ideal value, which is 3017. So the actual is 3059. So for expansion 9 to 11, we'll still use the same, but this time it's H9. So we have H9 minus H11. So H9 minus H11 actual divided by H9 minus H11 and solve for H11 actual using the same isentropic efficiency for the turbine. And then we can get the actual value of enthalpy at point 11 as 2805, which is also greater than the ideal value. And for expansion 9 to 12, so we have here 9 and 12. So we will use H9 minus H12 actual divided by H9 minus H12. Substituting the value of 12 from the table, we can get the actual enthalpy at point 12 as 2561, which is also greater than the ideal value. And finally, for expansion 9 to 13, using the same process, we can get the H13 actual. So this is H13 actual. So our H13 actual is 2267, which is also greater than the ideal value. Enthalpies as well as the actual value. Now we can use all of these actual value as well as the other value that we got from the different points to get the extraction rate. So after tabulating the values, the next step is to really determine the value of the extraction. Since we have 3 feed water heater here, then we also have 3 extractions, X, Y, and Z. So we are going to use energy balance to get the different extractions. First, at the fed water 3. So feed water 3, we have entering at point 10 is M10H10. At point 6, we have M6H6 and leaving at point 7 as M7H7. So using energy balance, energy in are M10H10A. So that we are going to use the actual value at point 10 as M6H6 equals to the energy out, which is M7H7. And then using the value of masses in the table, we are going to replace these masses here so that they will be the same terms. So we have it here. And then we can cancel out the masses so that we are left with this one. And then we are going to combine like terms. So we have this one. And then our x will just be equals to H7 minus H6 over H10A minus H6. So we substitute the values of enthalpies from the table. So our x is equals to 0.0421. So the rate of extraction at point 1 is at point 10 is 0.0421. Now we are going to determine the rate of extraction at the fed water 2. So we have here 11 coming in as well as 4. And the leaving is 5. So we have energy balance is M11H11A plus M4H4 is equals to M5H5. So putting in the values of masses from the table, we have this one. So we have M11 is equals to My. So we have M4 is equals to M1 minus X minus Y, and then M5 is equals to M1 minus X. And then we can cancel out the masses. And then we are going to combine the terms. So we have this one. So x and y and the left term. So we substitute the value of enthalpies, H54, 11A4, and 54A. And then, since x is already solved, we just substitute that also. And we can see that y is the only unknown. Then y, therefore, 0.0939. And finally, for the rate of extraction at feed water 1, which is z. So coming in are 12 and 2. Going out is 3. So that's why we have 12, 2, and 3 using the same process. So substituting the masses, rearranging the term to arrive with a value. Then substitute the value of x and y, which computed also a while ago. Then the only unknown will be z. So our z will be 0.090892. So from that, therefore, our rate of extractions are x is 0.0421, y is 0.0939, and z is equal to 0.892. So that is the one of the unknown from the problem. The next unknown is the mass flow rate. So for the mass flow rate, we are going to do energy balance in the entire power plant. So for the entire power plant, you can see here the heat input in the boiler is shown here. And we also have the heat input in the condenser. It's also shown here. And then we have the work output in the turbine. The work input at the different pumps, 1, 2, 3, and 4 are also shown. So for the energy balance on the entire system, energy in are your heat input in the boiler and the work input in the pump. The energy out are the heat rejection in the condenser and the work output of the turbine. So we are going to rearrange that. You can see this term. And this term here is just equals to work turbine minus work of the pump, which is also equals to work net. So net work is the work turbine minus the sum of the works of the pumps. Therefore, our work net can also be written is just equals to the heat input in the boiler minus heat output in the condenser. And since the work in the heat input in the boiler is mass flow rate times change of enthalpy H9 minus H8, and for the condenser, the mass flow, which is 1 minus x minus y minus z times the mass at the condenser flowing in the condenser times that enthalpy difference H13 actual minus H1. So that's why if we rearrange that, we can get the value of mass. And since we are given from the problem that work net is 1000 megawatt, so our mass flow rate is just equals to the equivalent in kilojoules per second of megawatt divided by all the value here. We substitute all of that. So we can get the mass flow rate as 1018 kilogram per second. So per second, the mass flow rate of steam is 1000 kilograms. So that's huge. Next is the heat supplied. So we are going to do energy balance at the boiler. So in the boiler, we have heat input M8H8 as well as heat input QB. Energy out is M9H9. So that's why we have it here. Rearranging the term, we arrive this one. And then we just substitute the value that we already have. So the heat supplied in the boiler is 2610.417 kilowatt. For the flow rate of the fuel, if the energy release is 35,000, so this energy release is from the fuel. So this energy is the same energy that we use for heating the boiler. That's why the heat from the fuel is absorbed by the boiler. We can do energy balance also that the heat input in the boiler is just equals to the heat released by the fuel, QF. And the heat released in the fuel is just mass of the fuel times its heating value. So the mass of the fuel is just heat input in the boiler divided by the heating value, which is given 35,000 kilojoules per kilogram. So if we substitute this 35,000 kilojoules per kilogram, we can get the mass of the fuel as 74.5 kilogram per second. Meaning we need 74 or almost 75 kilogram of fuel per second in order to maintain the boiler. And finally, for the cycle efficiency, that is just equals to work net over the heat input. And we already have those values, so we just substitute. So our thermal efficiency for this 3 open feed water heater regenerative cycle, which is actual, is 38.3%. So the reason why it's lesser, because it's an actual